Hey, it looks like someone else is actually here. Oh, wait. Can you all hear me?
Yes.
Yes. Okay.
Yes.
All right. Can you all see my slides? I've got it on my Mac.
Yeah, everything looks fine.
Okay. Cool. So we need to wait for a few more people to join. Is it okay if we don't start right at 3?
Sure. Who are you? Yeah, that's fine.
Okay. Okay. Also, I'm gonna keep my video off as usual. I'm on the phone with the audio and with the screen sharing on the Mac. So I just want to make sure that there's sufficient bandwidth going through my phone. So video sharing tends to slow that sort of thing down. So.
Who are we waiting for?
I believe Josephine. I don't think Josephine's joined yet.
Oh, okay.
I invited a couple of other people who are going to be here, but if they want to join afterwards, minimum we need everyone on the committee. So okay, it looks like everyone on the committee is here. So do you think I go ahead and start, or do you want me to wait a few more minutes? In
Oh,
order
I think you should go ahead and start, I think.
to start. Okay. All right. Please let me know if my slides for some reason don't come through. Like I said, I'm on the phone on one hand and I've got screen share on the other, so I'm not going to be paying attention to both at the same time. Okay. So hi, I'm Maxie Schmidt. This is going to be my PhD oral exam. Um, Glad that you all could join me. Let's see. I titled it Factorization Theorems for Generating Special Sums. So I want to again thank my committee members for taking the time to help me out and sit on the committee and do this. You can read who they are. Um, okay, so first of all, I'm going to give some overview and goals for the talk, an overview and some goals for the talk. Um, So in the next several slides, I'm going to hope to motivate why generating function-based approaches to basically generating or enumerating special sums is going to be useful in applications, why it's sort of a nice combinatorial thing you can do in certain circumstances for certain sums so far. I'm going to identify a general method for expanding out the generating functions of special sums, and this is motivated by the first example I'm going to give. So I have a number of publications already related to these so-called factorization theorems. So basically you get like a matrix-wise fit factorization out of these, and you'll see that in a few slides. And then I'm going to also highlight some new approaches to this moving forward and some aspects that I'm going to be looking at ideally in my thesis research. Um, it also brings up some questions about the most natural ways of forming the generating function-based expansions for these generating these special sums. Um, So we'll look at basically the typical example, which is the first thing that ended up in one of my publications related to this, and then sort of address the best way or like a canonical way even to go about expanding these sorts of things, like which generating function should we pick in expansions, and I'll point that out along the way. Okay. All right, so first of all, I'm going to give some review and definitions just to make sure everyone's clear on notations and recalls the specific definition of a generating function I'm going to be giving. So recall that an ordinary generating function, which I'm going to abbreviate OGF, of a sequence, so just fn for n greater than or equal to 0, or equivalently, you could say an arithmetic function, so a sequence, maybe even an integer sequence necessarily, but not necessarily, um, is defined by the following sum. So it's going to be f of z is equal to that sum. So we can write the series coefficient extraction operator using the notation there, the bracket notation, which is common in some context. So in particular, the concrete mathematics book, which I'm a big fan of, uses that notation, so I'm going to use it here. It just means that if you do bracket z of n, you're talking about the coefficient of z to the n in the power series expansion. Okay, so there's a couple of ways you can look at generating functions. The way that I typically focus on them is going to be as formal power series. So you're going to get expansions that really, it doesn't matter what the radius of convergence of z is, where this converges, you're just going to treat it as formal power series. So I'm going to use the analogy here just to remind everyone from Wilf's generating functionality book. Basically, like the powers of z are going to hang coefficients on them like series, like clothes in a clothesline. That's the analogy they give in that book, which I really like. And that's sort of the formal power series way of looking at this. Alternately, we can look at f of z as an analytic function and justify properties like asymptotic expansions, which you can get out of that. Hold on just a second. Sorry, my phone is saying that I have a low battery. I'm going to make sure that it's plugged in. Sorry about that. Okay, so again, the analogy of the clothesline, which is what I like to view these sorts of expansions as, is again formal power series, is going to be out of the generating functionality book. All right. Okay, so I'm going to go over a motivating example, which motivates the particular sort of matrix-wise or matrix-based expansion, the factorization theorems I alluded to earlier. So this has appeared in a couple of publications of mine. We focused on basically generalizing different aspects of this and writing out in a couple of different ways. And you can see the references when I display the references, which publications you can refer to afterwards if you're interested in looking more at this sort of thing. Okay, so the so-called Lambert series factorization theorems. So this is going to be, in some sense, with respect to at least my work on this sort of thing, the first and prototypical example. This is going to be what motivates this type of expansion, because you get particularly nice properties out of writing it this way in these cases. So this idea, again, was based out of some combinatorially themed work I did with these generating functions that I first published around 2017. I think I did the research for it sometime in 2016. Then I was contacted basically over the ResearchGate site by Mircea Mirca, who's a Romanian mathematician, and I ended up collaborating on several papers with him. A couple of them got published in the Ramanujan Journal additionally, and also we published an article in the American Mathematical Monthly, which is related. Okay, so what this particular example is going to do is it's going to relate multiplicative number theoretic functions to more additive functions like the theory of with the functions you'll see in theory of partition. So in like George Andrews' book. So the reason this is going to be particularly useful is something we'll see in a couple of slides, but basically it's sort of a way to give a generating function expansion for multiplicative functions where you typically can't just do the typical OGF type thing. You have to basically formulate it so that you get divisor sums out of it, and then you get nicer properties. Okay, so again, I'm going to review some definitions. So multiplicative functions, just to remind you what that is. Recall that an arithmetic function f is called multiplicative if f ab is equal to, you can basically split it up as long as the a and the b are relatively prime. So some typical examples of multiplicative, sometimes completely multiplicative, where it's not going to matter that the a and b are completely prime. You'll always be able to split it up that way, and that's going to be the last definition or the last example I give. But some multiplicative functions would be the Mobius function. So mu of n which is basically a signed indicator function, as I like to call it, of the square free integers. So when you square the Mobius function, you get the indicator function of the square free integers. Otherwise, it's signed with respect to the weight of how many distinct prime factors there are. So Euler's totient function, so phi of n, which you see just all over the place in math in general, is going to be defined by a sum like this. So this is another special sum type, which is not necessarily a divisor sum, but you're going to sum over the integers in the range one d less than or greater than or equal to 1, less than or equal to n. Uh, whatever you relatively find n, you're going to this is the kind of number of functions or number of integers in that range that satisfy that. They're also in general case sum of divisors functions. So sigma sub alpha of n, which are defined by that particular divisor sum. So the notation d and then the slash or the mid symbol n just means to sum over the divisors d of n. So and then you're going to basically sum n is going to be d to the alpha. So it brought to my attention recently, actually, that alpha can be complex valued, and then you have to consider things like branch cuts. But we're just going to assume that alpha is a real parameter. And so I've done some research on these separate research, like generating function-based expansion. Why this particular example is going to be interesting to me. So a special case of this is going to be the divisor function when alpha is 0, and then sigma of n, which is related to things like perfect numbers and other things, is going to be the special case. And then the last example is going to be the Louisville lambda function, which is completely multiplicative because this thing is completely additive, or the omega function is completely additive. So the omega function, omega of n, big omega of n, and then minus 1 big omega of n, a part of that definition, is basically going to count the number of distinct prime factors, including multiplicity. So just a quick reminder on what that notation means. Okay, let's see. So what exactly is a Lambert series generating function? So I want to make sure that we're very clear on what a Lambert series generating function is, as far as I'm going to define it or consider it in the next example. So Lambert series generating function is typically it's just called a Lambert series. But here's what it is. It's a construction that basically, again, generates series related to multiplicative functions, which typically occur in like a number theory, like multiplicative number theory or number theoretic context. So formally, what the definition of this is, and I don't think I do have a pointer. Let me see. Yeah. So this definition here is going to be L sub f of q is going to be so you're going to sum over f of n, sort of like the typical generating function you would, but you're also going to have the denominator factor in all of this. And when you expand these things out in terms of geometric series, so the qn over 1 minus q to the n, what you get is very easily the right-hand side expansion of this, which is going to be a divisor sum. So d dividing m, and then you're going to basically convolve. This would be like a Dirichlet convolution of f with itself, is what's going to be generated by these generating functions. And then formally, you're going to take q less than 1, but we're going to basically treat these things as formal power series and not really worry about that restriction in the text. Okay. So some examples. So there are lots of examples of these. And I actually recently wrote up something that ended up on the archive, which is catalog of Lambert series identities. So that's in the references. It's kind of cool. It's actually one of the first things if you search for me, one of the more recent publications that some people seem to like, or I guess things on archive. So this first one, 1a, is going to be the Lambert series of the Mobius function, and you get just q out of that. And there's a reason, because when you convolve q or the Mobius function with 1, you basically get the Kronecker delta symbol or the multiplicative identity with respect to Dirichlet convolution. So that's reflected here. So the Euler totient function. I'm sorry, could you excuse me for just a second? I've got something in my office that I need to take care of just really quickly. Hold on. Sorry. So the function, which is going to be the 1b, that Lambert series expansion, there's going to be a divisor sum identity, which basically gives you n. So when you sum over n or take the derivative of just the ordinary geometric series, you're going to get that sort of expansion. Inside of 1b. supervisor's function is the
Maxi, the your audio is sort of comes across as muffled from time to time.
is it?
Yeah, it can be a little hard.
Okay, I'm
Some
sorry.
sentences are a little obscured.
Okay, do you want me to start over on this slide or go
No,
back?
no, just maybe just think about your mouth where your phone is.
Okay, where my phone is. Yeah, let me hold the. Is it clearer to hear me now?
Sure.
Okay. Okay, I'll just hold the phone. Okay. So can we start from 1C or you think that's
1C is
fine?
fine.
Okay. So 1C is going to be the sum of divisors function generating function. So to get an ordinary generating function here, um, on the right-hand side, you're going to basically form the Lambert series generating function or the LGF of n to the alpha. And then, of course, you get the convolution identity that defines these functions there. The legal lambda function in 1D, the LGF of that is going to give you q to the square powers here. Okay, hold on just a second. Sorry, we're having technical difficulties. In 1E, basically, if you do this, this is one of the another divisor sum identity you can get in several books, like Hardy and Wright, for example. Um, so the indicator function of the square for integers, when you take its LGF, you get 2 to little omega function, which is basically going to be an analog to the big omega function that I just defined, except you're basically going to count the number of distinct prime factors of, in this case, m, without multiplicity. So just the number of distinct primes that divide it, no multiplicity counted. Okay, so let me move to the next slide then. So some useful properties. So these are in the catalog article I posted to archive recently. I submitted it somewhere else. But just kind of motivating why these things are useful. Yeah, I'm sorry. It seems like there's some background noise. Is that my phone or is it? Uh, okay, yeah, right. So some useful properties. If the function f has an ordinary generating function, again, I'm going to abbreviate it OGF just as a reminder. So f of z defined by that series. In this case, we're only going to index over n greater than or equal to 1. The natural number is n greater than or equal to 1. It's going to be related to the LGF by the identity in the first bullet point. So L sub f of q is generated by this identity. So it's not that difficult to prove. There are a couple of other things you can do, like relating the LGF to the ordinary generating function. There's an integral transformation, which you can read about in that reference if you want to. That's kind of a cool relation to this, which is there's a definite relationship between the ordinary generating function and the Lambert series generating function of any given f. So let capital F of x, and I just realized that this is very bad notation, but basically it's typical to write the summatory function when you take the partial sums of the little f and you write it with the capital F. But this is a different notation than in the first point. So if capital F of x is a summatory function of f, then we're going to have basically a generating function for that summatory function, which is given by the next identity. So you take the Möbius function of it, you take L of f, you give it the input of q of n, and then you divide through by 1 minus q, which is sort of a typical generating function type construction to begin with to form the summatory function. But in this case, we're going to relate it to Lambert series generating function. Okay, the last point, some other useful properties of these Lambert series generating functions. If you have a subset of the positive integers given by a here, and its indicator function, which is basically just going to be 0 or 1, depending on whether n is in the set. So this notation, chi sub a, is what I'm going to use. Then we're basically going to have that this identity holds. So you can get a generating function for just the q, unweighted by any coefficients, just the q that are in that set, are going to be given by the left-hand side here. And it's not too difficult to prove. Again, this is in the catalog article, which is going to be shown in the references. Okay, so again, just motivating why these things are useful outside of, just like pure number theory kind of thing. They've got some interesting properties. So, okay, last review slide, I believe, is going to be the partition function, just to remind everyone what P of n is. This is probably the most common type of partition function, but again, a lot of these things come up, and typically like products that generate different partition functions have different properties, but this is probably, this is the one we're basically going to need to understand the example that I'm giving. So a partition of a positive number n is a finite sequence of positive integers whose sum is n. So more formally, you can write this out in terms of lambda i's. So basically the typical partitions are like the components of the partition. And these, they're going to be defined. You can order them in this way, and that should be lambda, this should be 2, and the 1 lambda 2, and then lambda k. such that their sum is equal to n. So you can define it that way. That's another way of doing this. The precise definition of the function p of n is going to be the total number of partitions of n. We're going to define p of 0 as 1. Okay, so for example, p of 5 is equal to 7, since the number of distinct partitions of 5 are going to be listed as follows. So 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, and so on. There's 7 total basically decompositions where you basically disregard order and you write them using this sort of inequality. Okay, so by combinatorial argument, which I'm not going to give here, but with products of geometric series, we have that the ordinary generating function for Pn is going to be given by the reciprocal of the Q-Pochhammer symbol. So it's going to be in this notation, and it's going to be this expansion right here. So again, Q of n, the bracket notation is going to extract the coefficients of the generating function right here. Okay, so here's where this ties into the initial example of this sort of expansion I wanted to cover in my presentation. So some work on Lambert series factorization theorems, so termed factorization theorems, which is what they're called in some of the articles I've got. So we're going to say let S sub E and S sub O, and then parameterized by n and k, respectively denote the number of k's in all partitions of n into an even, respectively odd number of distinct parts. Then we're also going to let this notation, this infinite Q-Pochhammer symbol, defined this way. So parentheses A and then Q and then sub infinity, it's going to be defined by this infinite product. So in the previous slide, we're going to set A to Q, but it's not necessary to do that. So A could be plus or minus 1. A could be any number of things. It could be Q squared, for example, gives another partition function, generating function. Then what we're going to get with these definitions in mind is this expansion, this type of expansion of a Lambert series generating function right here. So we're going to write it in this sort of decomposition. So this is the Lambert series generating function on the left-hand side that we've already defined and looked at some examples of. And we're going to use this expansion to basically factorize it. So what I mean by factorization is, again, sort of a matrix-based factorization. So these terms right here are going to form a lower triangular matrix, and it's going to be invertible. It's got ones on the diagonal, and it's very, very, very closely related to partition theory. And then we're also here, we're going to have this term 1 over the infinite Q-Pochhammer symbol is going to be another partition function generating function. So there's sort of a natural relation here between the sort of multiplicative construction you get out of a Lambert series generating function and then partition theory, which typically don't go together. It's very rare in the references that you're going to see this sort of thing. So it's sort of an important interpretation. And one way of looking at that is why we get that sort of relationship out of this. Okay, so I'm going to continue on with that point in a few slides, but I'm going to continue on also motivating the expansions that I'm looking at. So we're going to rewrite the previous factorization theorem in the following form. So we're going to have just the normal Lambert series generating function expansion of f, so the LGF of f, and we're going to write it this way. And then we're just going to write that lower triangular matrix as S sub n k, and then we're going to multiply it by fk, and then we're going to take the partial sums as the coefficients we get out of this. So again, this is a lower triangular sequence, and it's going to be an invertible matrix. So we're not looking at like infinite matrices or any sort of infinite dimensional matrices, but when you take a finite dimensional matrix with whose entries are going to be given by these S sub n k, you're going to get a lower triangular sequence. So they're going to be generated. It's not difficult to see this. It's very, very simple argument, but I'm not going to go through all of the details. So how you generate these matrix entries are going to be S sub n k is given by the coefficient of this generating function. So you're going to have this term in the Lambert series, and you're going to multiply through by the just ordinary infinite Q-Pochhammer symbol. So if you start looking at these things with Mathematica and you start doing some computational experiments and experimental mathematics with them, by inspection, we're going to have the inverse matrices, which I'm going to denote this way, S sub n k, and then just -1 superscripted. It's going to be also related to partition functions. So here's the intuition for this. If you want to look at this table really carefully or just sort of skim it, I've already highlighted the points where you're going to see the partition function value. So at the bottom of the slide, there's going to be the first several values, just to recall what the first several values of Pn are. And then we're going to see that this lower triangular sequence very closely related to it. I also have in pink, there's another partition function which is common, but it turns out not to be related as carefully to this. So I'll just let you all observe that for a second, just to give you a chance to look at the slide and the diagram. Okay, is it okay if I move on? Yeah, okay. Okay, so a precise formula for the inverse matrices is going to be given by the first point. This can be proved by Möbius inversion, but it has this exact divisor sum. So we're going to take S of nk, we're going to weight the divisor sum, basically a convolution, but it's going to be shifted with respect to k here, partition function times the Möbius function. Um, the matrix inverse turns out to have the Lambert series generating function given in the second point. So here, just going to be q to the k and then over the infinite q Pachymer symbol. So it follows from the first formula in the first point of the slide that for all n greater than or equal to 1, we can completely invert this construction and solve for f of n exactly by the following thing. So this is sort of like, on the one hand, we have that we're enumerating with the Lambert series. In the expansion I gave in the last slide, we're enumerating those divisor sums, so f convolved with 1 basically. And then in this case, we're going to do like a matrix-wise and invert for the coefficients, and this is what we get out of it. Is this formula at the bottom of the slide. Okay, so let me move on to the next, let's see, next slide. Okay, so this is, again, I've alluded to this, I think, twice so far. The relation of the matrices you get in this sort of factorization, again, I'm going to call it a factorization, brings up a natural question, which is, why is it so convenient that the S sub nk and the inverse are related to partition functions, especially when the construction of a Lambert series generating function basically gives you sort of a convenient structure to express multiplicative functions and convolutions with those, which tend to lead to nice multiplicative structure, and then you have a much more additive structure with the partition function. So not in the sense of like an additive property or an additive function in number theory, but in the sense that it's going to count the number of ways to basically sum up into different bins, taking the parts into different bins. So when we go through and generalize this sort of construction, and which I'll do in the next couple of slides, you want to ask, or at least something that I'm going to ask, is why did the partitions fit so naturally with the multiplicative function LGFs that we defined above? And what is going to be the most natural way to expand things out in the context of other sums, sort of special sums that would arise in applications? It'd be interesting to have a combinatorial interpretation of a generating function for these sort of special sums. What exactly is the most natural way to expand things out? Okay, so just please keep that in mind when we look at the next examples. Okay, so I'm going to generalize the sort of factorization theorem more generally for other sums in the next slide. Okay, so this first point, which it looks kind of intimidating until you sort of just walk through what exactly it is that I mean here. So when we started generating the coefficients of the Lambert series, you get divisor sums out of them. So that's going to be a subset of the integers in the range 1 to n for each coefficient of n, or q to the n. So here we're just going to take another subset of that range, and we're going to call this a sub n. Here is all I mean. So like the totient function, for example, the precise definition of the totient function is going to be the relatively prime integers to n in that range. So that's another example here. But we're going to look at generating sums of this form. And then on the right-hand side, where we had an infinite q Pachymer symbol, so again, with respect to, we want to kind of generalize, maybe partition functions are not the most natural way in the context of each particular special sum case we can look at. So we're going to do a 1 over CQ, where C at 0 is not going to be 0, so it's not going to vanish at 0. And we have a matrix, which is going to be highly dependent on the C, highly dependent on the choice of those subsets A of 1 to n, and then we're going to basically write it out in the same form. So this is going to be a lower triangular matrix, ideally invertible, but it's going to depend on those definitions of the A sub n. The matrix entries are again going to be generated this way. So I gave an example in the Lambert series generating function case, but in more generality, this is basically how you're going to do this in the second point. So again, we're going to have this natural question: what is a good choice, quote, good choice in generating function C given in the definition above? It's going to be with respect to those sets A sub n. And we want natural formulas. So again, sort of a canonical representation, maybe partition functions. I mean, they're definitely analogs. If you use the infinite q Pachymer symbol as your CQ, then you're going to get partition-related things, but maybe that's not the most natural way of writing this. So it brings up some questions that I want to eventually look at and sort of, justify why this would be the best way to write it out and why there's a natural expression for certain C given the choice of the A sub n. The inverse matrices of these S sub nks, and again parameterized in the A and the C, are going to be basically very closely tied up to generalized forms of Mobius inversion by special Mobius function, which are going to be problem specific, basically. Okay, so we'll see an example of what I mean by a generalized Mobius function and what I mean by that in the next slides. Okay, so some examples. We're going to provide several examples of these special sums. Sorry. And inversion operations on them. So we're going to, there's a good book that I found more recently than I was looking at these for the Lambert series generating function cases, which is in the references, but it gives it gives a nice chapter on generalized Mobius functions. And I'm going to just basically list some of my favorite examples out of that book or that chapter. They're called A convolutions, K convolutions, B convolutions, and then there's some matrix generating convolution sums, which are very natural for what I've been doing. So again, we're going to generate this sort of thing, and I'm hoping to look at these specific examples and more generally find some nice properties of the analogs to the Lambert series generating function expansions I've found so far. All right, so here are some examples. Okay, so the A convolutions, which are basically restrictive Dirichlet convolutions and divisor sums, are going to be defined as follows. For each n greater than or equal to 1, we're going to let A sub n or an be defined as some subset of the divisors of n. Okay, then we can define the A convolution of f and g, which again is an almost direct analog to the Dirichlet convolution, where A sub n is just all of the divisors, is everything possible in this set that we could take. So the largest subset of this set. It's going to be defined this way. So you're going to sum over all the d in that set, and then we're going to do this. So f of d and then g, we're going to multiply by g at n over d, which is another divisor of n. So we're going to say that a natural number n greater than or equal to 1 is a primitive if A sub n is basically 1 in n. Okay, so under the list of assumptions, so the resulting A convolutions are regular convolutions, which is a very sort of complicated, yet sort of natural if you think about it, definition in the book, which I'm not going to get to. We get a generalized multiplicative Mobius function. So mu sub A at P of alpha is going to be defined as in the following cases. So it's similar to the normal Mobius function definition. This construction leads to a generalized form of Mobius function between the A convolution, or Mobius inversion between the A convolutions. So just to remind you, I'm not going to state it precisely, but the classical Mobius inversion takes the following form. So g of n is equal to this divisor sum f convolved with itself, if and only if f of n can be given by this default divisor sum. So basically the convolution of g with the Mobius function. Okay, so I'm going to move along. That's one way of looking at this, or one sort of example that I can look at. There's so-called K convolutions, which are divisor sums of a little bit different form. So let the function K be defined on tuples of the natural numbers, and then on to C. So whatever it is that the function gives, we define on all ordered pairs n d such that n is greater than or equal to 1 and d divides n. So we define the K convolution of two arithmetic functions f and g to be the following sum. So the sum over the divisors of n, it's sort of a weighted Dirichlet convolution, basically. So it's the typical terms you would get, the convolution of f with g, and then we're going to weight it by these k and d's. Okay, we can define the generating function factorizations of these sums in the following form again. So again, it looks kind of complicated and intimidating until you break it down and you think about the first example I gave of the Lambert series generating function factorizations. It's going to be, these sums are generating as the coefficients of, again, we're going to take 1 over this, where we had the Q-Poch-Hemmer symbol, we're going to insert a C of Q, which is going to ideally be a natural interpretation with respect to whatever problem type we're working with, which is application dependent. And again, I'm going to look into what the most natural sort of representation of that would be. Then we're going to sum m greater than or equal to 1, and then we're going to look at these matrices. And you weight by f of k, and then the typical generating function enumeration of this term and these coefficients. So again, the form of these E sub n k matrices, which again are going to be parameterized dependent on the k, the choice of the generating function c and g. So notice we have an f of k term here, so it's not going to depend on the f, but it will definitely depend on the g, because the g is the remainder of the terms. It's going to be highly dependent on the k. So again, these are very problem-specific type things, and I hope to look at these special cases and get a more general or meaningful or interesting general theorem on how to expand these things out well. Um, Next example are going to be these so-called B convolutions, which is a nice example. I like this. So if you let nu sub p of n denote the maximum exponent of the prime p in the factorization of n. So we're going to define these b sub n d's, this function on the tuples of natural numbers n and d by the following prime product. We're going to take the binomial coefficient, and in the numerator, we're going to take that function at n, and then we're going to take that function at d as the second lower index of the binomial coefficient. Again, when I write p divides n, it's not just the divisor sum over n, it's the primes p dividing n. Okay, then we're going to get this sort of inversion formula. So we actually have this, and it's provable. It's in the book I referred to, which will be in the references if you want a precise proof. But f of n is equal to this divisor sum, where we're weighting the g sub d's by b sub nd. If and only if g of n is equal to this divisor sum, where we're going to weight the f of d's by the Liouville lambda function, and again the b sub nd's. Okay. So yeah, that's another example. That's another interesting example that motivates this sort of thing. And again, what we're trying to do is find a meaningful, or like combinatorially meaningful generating function expansion that gives additional properties of these types of sums, or is more revealing towards properties of these types of sums. But this is just the example of a special sum that we can look at in this way. Okay, so finally, my last example is going to be the matrix generating convolution sums example. And I'm going to give two particular examples or special cases in the next slide. So let G be the matrix, be an infinite dimensional matrix in this case, containing only the elements 0 and 1. So basically, it's going to denote inclusion of a specific, like, lower triangular index. So suppose that G sub I j is equal to 1 if I equals j, and, or maybe I did. No, I'm sorry. This is a different. Okay, I'm sorry. This is. I think I have a typo in my slides actually. Okay, so the idea is going to be the next points. I'm sorry. Furthermore, let the ones in the column n of g appear in the rows, in these rows, where we're going to have this sort of ordering on them. We can define the convolution of two arithmetic functions f and g according to basically inclusion by the matrix in this form. It's going to be this type of convolution sum. So whereas we were summing over divisors or divisor subsets weighted by like b or k here, we're just going to do the convolution of a and g, or f and g, where we take these indices. Okay. Right. And okay. So examples and special cases of this definition. So we can take the divisor sums and divide the divisor sums as a special case of that sort of matrix-based definition. The convolution star sub d is the same as the Dirichlet convolution in this particular case. If we want to look at things like Euler's totient function, which is something else, another fellow graduate student and I have done some work on, and it's forthcoming. There's a revision in the Ramanujan journal that we've submitted so far about this sort of research, but you can do this sort of generalized sum at the bottom. So this is going to be a case of these matrix generating convolutions, where you look at the relatively prime integers. So I and j, GCD of I and j is equal to 1, then you're going to give 1, basically. And so if f is 1, you get the totient function out of this definition. And there are ways to generalize Euler's totient totient function very naturally, and you can similarly see things like that by setting f to the appropriate function. Okay. Directions for future work. This was sort of suggested that I add this very quickly. I think that I'll sort of clarify the direction I'm hoping to go in with this sort of expansion and what I hope to do with it. Okay, so the interest of mine, again, started with the generating function expansions of Lambert series. So I had some natural interest in this. I was just looking at these. I have a few articles. Some of them are under review still. Some of them have been published, which are going to be in the next slides. And then we looked at some generating functions with another collaborator of mine, a fellow graduate student at Georgia Tech, a year or two ago. So basically, there's a natural interpretation. So I mentioned that it's sort of unique. Lambert series generating functions are going to give you a nice sort of typically combinatorial construction of a generating function. You get Lambert series is going to help you generate more multiplicative functions. So in the sense of like a Dirichlet generating function or a DGF, which is another generating function type, sans the Q, is going to give you the typical like powers of Q close hanger hand on certain functions by taking a series. So the new interpretations of these natural expansions, like relations of the multiplicative functions and divisor sums to partition functions, which again, that's sort of a curious relation. How do you get partition functions naturally related to these multiplicative function cases and divisor sums of them? Um, We'd be looking at more like canonical type expansions, like why was it so natural in that particular example, and how do you generalize it to specific other applications? So what is the most natural way of writing those generating function expansions? That's something I'm going to be looking at. I have a few ideas on that, but it's going to be not covered in this presentation. All right, let's see. So the sort of work and those type of expansions I defined more generally is going to give insight into special sums and applications from a typically combinatorial related construct of generating functions, which is a nice way of looking at things in general and where you might not have a natural generating function type. Again, so for certain multiplicative functions, there's really not a nice way of writing out their generating function. So we're going to basically sort of force it, but in a way that's very intuitive and has some revealing properties and structure to it. Another sort of not completely disjoint direction, but sort of thing like in a binomial transform and Stirling number like generating function transforms, you get some nice properties and relationships and functional equations out of the generating functions when you do this. I expect that there will basically be some related identities in that case. So that's another direction of this. Okay, so I have several other slides. I think I talked maybe more quickly than I had intended to over these sort of topics. Is it okay with you all if is the presentation long enough, or do you want me to go into some more examples? I do have some other slides prepared. Anyone? Do you want me to keep going for 5 minutes, or is that? Okay, I think that it's been about 40 minutes, which is the my
Yeah, it's
examples very very thoroughly.
so. Well, Maxi, this is a very poorly framed question.
Okay, yeah.
Is there some sense in which there is a simplest generating function representation?
Of
You
any
have
particular,
all of
what would I
I mean,
like a canonical generating function or something or like that? Is that what you mean?
well, I mean, you have all of these different approaches with,
Yeah,
and some of them extremely general.
yeah.
And I mean, so how do you choose?
That's a good way of asking that question, I think. So what you mean is in the context of the factorizations that I'm proposing to look at, or
Yeah,
do you
well,
mean?
you have these methods beginning from Lambert going sort of climbing a ladder of complexity in some
Yeah.
sense. I'm just
So
and I'm happy to say that it's a very poorly
there
worded
isn't
question.
I don't yeah, I don't know of a clear way to answer that. That's something I have to really think about. I have some ideas on why it was natural. Some identities. There's something called an Euler transform, which you look at in some like software packages on the online sequences database has a list of transforms. They published a paper on that sort of thing, which sort of makes why the partition function is going to be very natural in the context of Lambert series generating functions. There's a nice recurrence relation between the partition function Pn and the ordinary sum of divisors function. So when alpha is 1. So that sort of construction gives a nice product and that sort of relates that sort of thing. So more generally, when you take any particular type of sum, which necessarily is not going to be a divisor sum, and like in the special case I looked at, I really don't know yet. I have some identities that are suggestive of it, but there isn't really a clear answer of what a canonical sort of expansion would be, like how you would define those generating functions C of Q. Again, that's something I want to look at because it's sort of an interesting question. Um, did that answer what you were aiming at?
It was a very open-ended question. It's totally fine.
Hmm.
Okay, yeah, there's not a clear answer for that actually. It's not. I mean, it's very natural in that one example, which is why it was so interesting and why we ended up getting pretty good publications out of that. Which is it's not quite clear in full generality why partitions fit in so nicely with the multiplicative functions that you typically would enumerate with the Lambert series generating function. It's a very open-ended sort of research topic right now as well. So, um, okay, is that what you wanted?
Sure.
Okay.
Mhm.
Mm,
I had a question, maybe just to ask a little bit about, you have all these identities, and then I was just wondering, at the end of the day, can some of these identities help you say something for any of these functions, because they seem to be very general. So you pick your favorite
Yeah.
function. I mean, it could be the partition function, or it could be one of these multiplicative functions that you use, Euler, Möbius, whatever. Can you say, I get from this identity, I get a very classical result of
Um,
something? I
yeah. So
couldn't,
in
yeah.
some of the,
Mm-hmm.
I'm sorry, some of the papers with Mersa Merca, we gave several examples. So it's not entirely clear where in applications this is going to tell you something new, because again, this sort of representation or the sort of generating function expansion is going to not necessarily be dependent on f until you plug in a specific f. Um, if if it would be okay, can I get back to you with a list of examples from the papers to answer that sort of question and give you sort of an idea for the flavor of some of the things you can do with this? Because I didn't go into a lot of detail with that part.
Yeah, no, that's fine. But that would be for me a little bit, you do something, it's also nice to connect it to what other people have done and sort
Yeah,
of, generalize in one way or another. And also when you say factorization, by the way, on page 2, it was really confusing to me. I was thinking initially that what you would do, I mean, before I looked at the slides, that like
yeah,
you take, say, the Jacobi theta function. I mean, you have one series expansion on one hand, and on the other, you can factor it really as an infinite product. So that's something very useful. But what you do is completely different in a way. It's just to rewrite it in a slightly different way. And
yes.
what you say factorization is more like LU factorization of matrices, if I
Yeah, it's
understand
like a
this
matrix.
correctly.
Yeah, it's like a matrix. Yeah, it's like a matrix-wise factorization. It's like the product of the matrices. Yeah. So factorization theorems was not originally my terminology, but I went with Mercer's. He titled, so around the same time that I wrote the Acta Arithmetica article. And he had written an article related to the specific type of expansion that I first gave with the Q-Pochhammer symbol and the S sub E's and the S sub O's partition functions. He called them Lambert series factorization theorems. That's the title of his.
Yeah, I saw the papers. Yeah, I know that's how he called it.
Yeah,
But
that was his
okay,
terminology.
and is
But it's
there any
definitely,
connection to these Ramanujan identities, which are, have you had any connection to any of these beautiful and difficult identities,
sorry, which identities?
which are basically the Ramanujans?
No, I have not. I would need clarification for which identities of
Well, there are so many of them. Yeah, okay.
yeah, they're right.
That,
I've heard books, there are entire volumes of that. Yeah, but if we could, no, I really haven't. Maybe we could talk more about that after the presentation, if that would work.
okay, thank you.
Okay. Anyone else? Um, if no one has any other, if no one has any other questions for me, I guess that's the conclusion of my exam presentation. I'm going to post slides on my website, so let me go back up to where my website is. It's easy to find out the Georgia Tech math site, so it's basically the typical people.math.gotech.edu, and then this is my ID at the university. So I'm going to post the slides. So there will be a few other examples. Um, you all are always, anyone in the audience who's not necessarily a committee member is free to contact me about this if you look at these later and just want to know more about it. I'm happy to discuss this sort of thing. Um, okay, thank you for attending. I really appreciate it, and thank you to my committee for.
Maxine, there, I mean, usually the committee meets, but I'm not sure how that's gonna, you're the moderator of this thing.
Yeah,
And
this is not your typical presentation, is it? I
well, I don't
mean,
know.
is there any? Yeah,
I
this
think
is
it's
Do you
okay if
need
he
the
drops,
meeting?
but then there is a recording, so it doesn't really make a big difference,
Oh,
I
I
think.
see.
so you all. I mean, I don't
Thanks for
want to
the
sit in
clarification.
on my deliberation unfairly. I don't think that you all owe me having to record this. I am recording it. I wanted just a copy of it for my own records. I gave a presentation. I can look at it later. You might need to go onto the bluejeans.gotech site and create a separate like chat room for yourselves and just get back to me with like feedback on it. Is that okay? Or do you want me to leave the presentation? I can leave too. That would work too, but it's going to be recorded.
I think you can, I mean, oh, Chris, you're muted.
Sorry. I'd suggest turning off the recording now.
Yeah,
Uh,
me too. Just turn off the recording and just and then just sign out. That's the simplest, I think.
okay.
Just
The thing is that I have to
walk out
log
of the
into the
room for
doc,
5 minutes, come back.
walk out of the room. It's still gonna be recorded. I feel really bad about that. I don't there. It's an auto recording, so I don't know how to turn it off.
If
But
you
let me
click on the red button, it should turn off.
red button.
The blinking red button.
I'm on my phone right now. Let me see. Sorry, technical difficulties. I'm gonna call this. Um, let's see. Blinking red button is, yeah, for all my technical skills, I'm really not good at pointing and clicking. I think I've pointed this out too. Yeah, I'm not blinking red button. It's auto recording. It gave me a little like moderator voice of its own saying auto recording in progress. So um I honestly would suggest you all create your own Blue Jeans chat link. That's okay. I'm gonna leave the room and leave the
Okay.
conversation. Definitely,
Um,
I won't listen to this part of it.
Michael, could
But
you send an invite to the committee members?
Sure.
okay, all right. Thank
Yeah,
you.
it'll
I
probably
appreciate
be
it.
easier if I do that from my computer. And it's Chris, it's you, Josephine
Plowman.
And I'm
Plowman.
also Michael. Yes.
Okay, okay. I'll send you something right now. Josephine, thanks for your help with this.
Um, with what?
You didn't you meet with Maxie earlier?
Oh yeah, I did. I did. Yeah.
Okay.
So I guess we'll just drop this the meeting and then we'll join the meeting that Michael organizes
Oh, it's Josephine, Chris, myself,
and
and
Plummen
Plowman.
and maybe Plummen. I mean,
Okay,
it's
okay.
all right.
I've just scheduled it. Hi, Chris. Oh, shoot. Damn it. Okay. How do I, how do I, more options? Where, Okay. How do I modify it? Edit. Starts 3:45. What time is it?
4 o'clock,
No, I need the exact time.
3:53.
Crap. Edit. Edit. Why can't I just start it right now? Okay. Well, that's what it is at this point. Six. Sorry. Okay. Sorry. Yes. Am I not here? Well, I thought I scheduled this thing, but I seem to be the only one here. So now I have okay. Well, we have some rain approaching. We have some rain approaching.
So are you gonna, can I do vacuuming or do you need to have quiet?
Into vacuum soon. I thought somebody wanted to have this meeting, so I scheduled it, but it wasn't optimal in scheduling because I don't do it that often. And now nobody's at the meeting, so oh, for crying out loud.